Greetings and welcome. In today's video, we're going to continue a look at probability, specifically with binomial experiments. And I'm going to kind of describe what a binomial experiment is, how to calculate the probability of a particular outcome in a binomial experiment, and we'll look at some problems as well. So a binomial experiment is a situation that has each of these conditions being true. So each trial has exactly two outcomes. So it's an experiment that can be repeated multiple times, like flipping a coin over and over and over. There are only two outcomes, either heads or tails, right? There must be a fixed number of trials. So in order for this to work, I'm going to have to know how many times I'm running the experiment. So for instance, flipping a coin 10 times, I know 10 is the number of times I'm going to attempt it. The outcome of each trial must be independent. All right, so I have to have situations that are not reliant on one another, or the probabilities can't change from one attempt to another. And similarly to that last requirement, the probabilities in each trial are the same, right? So the probability of success in every single trial or attempt remains the same, and the probability of failure also remains the same. So some of the variables that we'll be using for this, n will be the number of trials, right? So if I was talking about flipping a coin 10 times, that would be the n. R will be the number of successful ways that event can occur, or, well, the number of successful ways we're asking about, I guess, is maybe the better way to say it. S will be the probability of success for a single event or single trial, and F will be the probability of failure for a single trial. So to calculate the probability of exactly R successes over n trials, we're going to do a combo n R, all right? So I'm going to find out how many ways can I succeed R times over n trials. I will multiply that by the probability of success to the power of those R successes, right? R is the number of successes. And then I'll multiply by the probability of failure to the number of failures. And the way I calculate the number of failures is the number of trials minus the number of successes would give me the number of failures. So let's look at a problem here. Let's actually consider that. So what is the probability of getting 3 heads when flipping a coin 10 times? Right? So this does meet the requirements of a binomial experiment. And let's just define some of our variables first of all. So n is 10, the number of trials we're doing. The number of successes we're looking for is 3. The probability of success for any particular trial, since this is a fair coin, is 1/2 or 0.5, and the probability of failure is also 1/2 in the case of a fair coin. So in order to calculate this, the probability of 3 heads out of 10 tries will be the combo of 10, 3. So I'm asking how many ways can I get 3 heads out of 10? All right, so there's a certain number of ways I have to calculate there. And now let's calculate the probability of each of those. So I'm going to take the probability of success and raise it to the number of successes we have, right, which is 3. And since they're independent, this is, I mean, if I was writing this out longhand, that would be 1/2 time for the first success multiplied by 1/2 for the second success multiplied by 1/2 for the third, right? So because they're independent, that's why I'm multiplying it the same probability repeatedly. So there's my successes raised to the third power, and for failures, the probability of failure is still 1/2, and the number of failures is 10 minus 3, right? The n minus r, which is 7. Okay, so let's actually calculate this out. So let's see, 10 combo 3 is 120. 1/2 to the third times 1/2 to the seventh, I guess, well, is going to end up being 1/2 to the 10th. In this case, because both of these probabilities are the same. But I'll just represent this as 1.125, and 1/2 to the seventh is going to be even tinier, 0.0078125. And if I multiply all of these together, I get a 0.1172 roughly. So I get about an 11.7% chance that I'll get exactly 3 heads out of 10 when flipping a coin 10 times. All right. So that's how we can use this formula to calculate these. Let's consider another example in which the successes and failures are not equivalent, or the probability of success. Let's say for 5, well, let's do over 6 free throws. So playing basketball. What is the probability of getting at least, let's say 5 in, if, let's say the probability of a single free throw is, let's make it, probably my ability would be 5%, where 1 out of 20 tries I'm actually getting it in. So I'm not very good at basketball. But so let's consider this situation. So so n is the 6 free throws that we're taking, right? R is actually going to be a little bit interesting. There's 2 cases for R. I'll come back to that in a moment. Let's see. My probability of success is 0.05. My probability of failure for a single shot is 0.95, right? 1 minus 0.05 is how I could calculate the probability of failure. Because I know that success plus failure always has to add to 1. So to answer this, probability of at least 5, or sorry, yeah, so I think this is going to be unlikely, is going to equal the probability of exactly 5 plus the probability of exactly 6 in, right? Right, so that's another way I could summarize this, breaking this into an OR situation. At least 5 means getting exactly 5 in or getting exactly 6 in. So I'm actually going to have 2 separate probabilities to calculate here. So let's break this down. So in this case, R is going to equal 5 or 6. I'm kind of having to calculate it twice is what I'm doing there. So let's calculate the probability of exactly 5. So I want to figure out how many ways can I actually have 5 successes out of 6. Multiply that by the success, 0.05, raised to the number of those successes, 5, multiplied by the probability of failure, and I have 1 failure in this case, right? Because 6 minus 5 is 1. So this is the probability of exactly 5 shots in. And then add to that the probability of exactly 6 free throws in, which I'm assuming is highly unlikely. But nonetheless, for the sake of this problem, let's pretend we're interested in that. So combo 6, 6, how many ways can I actually get 6 free throws in? Multiplied by 0.05 to the 6th, and then multiplied by 0.95, my number of failures, to the 0th. And I think you guys would agree that 0.95 to the 0 is going to equal 1. Right, so it's going to have no effect on that particular term. So combo 6, 5, I believe, is going to be 6. 0.05 to the 5th is going to be very tiny. Actually, maybe I'll calculate this whole probability out at once. Times 0.95 times 6. And I ended up with 1.78125 times 10 to the negative 6th. So highly unlikely. And then to that I'm going to add combo 6, 6 is 1. But once again, I'll calculate this individually. 0.05 to the 6th power times 1. Here I get 1.5625 times 10 to the negative 8th. All right. So I'm going to add to that 1, 2, 3, 4, 5, 178.125. And I get 1.796875 times 10 to the negative 6th when I add those together. To represent this as a decimal maybe that we're more familiar with, I always write a 0 before my decimal point, and with negative exponents. If you include that 0, 6 will be the number of zeros you need. So 0, 1, 2, 3, 4, 5, 6. 6 zeros if I include the 1 before or to the left of the decimal point. And then 1796875. So yeah, so I would be very unlikely to be able to get at least 5 free throws in. Right? That's not very likely. Let's ask a similar question. What is the probability, as just a follow-up, I guess I'll call this part B. I think I'll have room, yep. So what is the probability of, let's say, missing all 6? All right. So this is an exact situation, so I don't have to break this up into multiples. So this is going to be combo 6, 0, because I'm having 0 successes, so the value of R would be 0 here, multiplied by 0.05 to the 0th, because 0 successes, multiplied by 0.95 to the 6th, right? Because I'm actually planning on failing on all 6 occasions here. And this is a situation that, hey, it happens to me. I'll miss all 6 in a row. So how many ways can I fail 0 times out of 6, right? Or sorry, I guess how many ways can I succeed 0 times out of 6? That's actually equal to 1. That's equal to 1, and then I'm multiplying by 0.95 to the 6th. So let's calculate that, 0.95 to the 6th power, and I get 0.73509. So that is about a 73.5% chance that I will miss all 6 shots in a row. So not the best situation there. So the way these work, I just want to point out that it's actually not that difficult calculating some of these at least situations. You can just kind of add these separate terms together where you calculate the exacts all simultaneously. What if, actually, let me ask an interesting question. What if I added this question? What is the probability of getting at least 1 shot? Right? Getting at least 1 in out of my 6 attempts. So, I mean, I could break this up into the probability of 1 plus the probability of 2 plus the probability all the way to the probability of 6, right? But that would be a lot of separate calculations. The other way I could think of this is I just calculated the probability of 0, right, of missing all 6. And this plus all of these is going to be 1, right? All possible cases, right? Getting no shots, 1 shot, 2, 3, 4, 5, 6 shots. That's all possible cases represented. I already know this, and if I want the kind of, I guess, the complement, I would almost think of it, I could just do 1 minus the probability of 0, right? And that would give me the kind of opposite situation of this. So how could I do that? That's 1 minus the 0.73509. So that is going to equal 0.264908. So I actually have a 26.5 about percent chance of getting at least one in. Right, so I just want to point out sometimes in these situations it's easier to think of these in terms of their complement, like solve the problem backwards first and then subtract its probability from 1, then solving all of these separate individual situations. So that's just kind of an interesting way that you could solve these as well. So these are called binomial experiments. Once again, they only apply to problems that have 2 possible outcomes per trial, right? So a success and a failure. Or problems that can be reduced to 2 possible outcomes. So like if I wanted to figure out what's the probability of drawing a card from a deck and getting an ace of spades 10 times in a row, assuming I'm replacing that card every time, I don't have to try to consider the probabilities of all the others. I just have to say, break it down into what's the probability, the chance of picking the ace of spades, and what's the chance of not getting the ace of spades. So I could reduce it down to a binary situation, right, or a succeed, fail sort of thing. So yeah, as long as it fulfills all of these conditions, you can apply this sort of principle. And it does. This does, by the way, there are all sorts of connections between this and binomial expansions. You might wonder why the word binomial showed up here. And it also relates to Pascal's triangle, but I actually cover that in another course. So if you are interested in that, plan on taking pre-calculus maybe. All right, so thank you guys so much, and have a great day.